Good morning everyone, how are you? So today we will start with section 2. But before we start with section 2, we'll just revise quickly section 1. Okay, so here a visual concept about section 1.
A car moving in a circular path experiences acceleration even when the speed at which it is traveling remains constant. This is because acceleration depends on velocity, and velocity is a vector with both magnitude and direction. When the car moves in a circle, the direction of the velocity vector is constantly changing. Therefore, the acceleration, or change in velocity over the change in time, is also changing. Acceleration of this nature is called a centripetal or center-seeking acceleration. When the radius decreases, the direction changes more quickly and the experienced acceleration is greater. When the radius increases, the direction changes more gradually and the experienced acceleration is not as noticeable.
Okay, so the last part, it just talks about the equation of acceleration. We know that the equation of centripetal acceleration is v squared over r, right? Okay, so here they are like demonstrating the relationship between acceleration and radius. So when the radius increases, it means when the object moves along a circular path with more radius, okay, so the change in direction here will be less, so the change in velocity will be less, therefore acceleration is less. Okay, that's why radius is where in the denominator. Okay, so when the radius increases, acceleration decreases, and when the radius decreases, what means the radius decreases? Here our object is moving in a smaller circular path. Okay, so the change in direction of the velocity will be more noticeable in this case. So acceleration is a change in velocity, so acceleration will be more in this case. Okay, so when radius is smaller, when the object moves along a smaller circular path, the change in direction of the velocity is more, therefore centripetal acceleration is more. Okay, this is the relationship between acceleration and radius. And for sure we talked, girls, about centripetal force. Okay, since we got centripetal acceleration, so for sure we can get easily centripetal force, because every acceleration is caused by force according to Newton's second law. So F equals ma, we just substitute a by its value and we got the centripetal force equals to mv squared over r. Okay, and we made for sure many applications about these concepts. Today we will continue. We will talk about Newton's law of universal gravitation. See, Newton's law of universal gravitation. So here we are talking about a new law. Okay, we already, girls, learned about Newton's laws. We learned about 3 laws for Newton: first law, second, and the third. But there is one now very important, and it's called Newton's law of universal gravitation. We will talk about it in the details in this section. Okay, so in this section we are going to explain how Newton's law of universal gravitation accounts for various phenomena, including satellite and planetary orbits, falling objects, and the tides. So we will see how the Newton's law of universal gravitation explains all of these phenomena, like how the satellite goes around Earth, okay, how planets, all of them, move around the sun, how the moon moves in orbit around the Earth. All of these phenomena will be explained using this law. Okay, so apply Newton's law of universal gravitation to solve problems. First, so as I said, we learned about Newton's law of motion, but there is one more law to discuss, which is Newton's law of universal gravitation. It's possibly, girls, one of the greatest strokes of genius in the history of mankind. Okay, so we know that all the planets, as you can see here, they move in orbit around the sun. Okay, in a specific orbit around the sun. So what keeps them in orbit around the sun? Here, if we want to talk girls, look, they are moving in circular motion, right? The title of the chapter is circular motion. So we are talking about all objects in circular motion. So these planets are moving in circular path around the sun. Okay, so we said for any object to move in circular path, we must have a centripetal force, okay, that keeps this object in the circular path. We said without the centripetal force, the object will what? Will go out of the orbit, out of the circular path. I gave you many examples in the previous section. We talked about word ball, okay, a ball attached to a string. We talked about a car making a sharp turn, okay, around a corner. So I said in the case of car, the friction is what makes the centripetal force. It is the centripetal force, okay. And in the case of the ball, we said it is also the horizontal component of the force of the string, which we call it tension. Here in this example now, we are talking about planets. In this example, the planets all are moving around the sun. So what is the type of centripetal force that keeps these planets around the sun? So for sure it is the gravitational force, okay. So Newton looks at the motion of the planets in their nearly circular orbit around the sun and understood that the centripetal force causing this motion was precisely the same force that causes objects that falls down toward Earth, which is the gravitational force. So he understood, he explained this motion. He said that the force, the centripetal force here, is the gravitational force. He conducted an experiment to prove that, a thought experiment. So we will see it later. Planets are in free fall toward the sun in the same way the apple hit him on the head. So these planets you see, they are all in free fall toward the sun, the same way that the apple in a free fall toward the earth, okay. So orbiting objects, all orbiting objects, any object that orbit another object, we say that this object is in a free fall, okay. So the planets are in free fall toward the sun, the moon is in a free fall toward the earth, the apple is in a free fall toward the earth, okay. So all orbiting objects, we say they are in free fall. So objects such as apple and planets, they differ greatly in size, but the same concept holds true. We will see how. Okay. See, to explain this, Newton corroborated this concept, this notion, with thought experiment. He said, consider a cannon sitting on a high mountain top in the figure here. So here, when the cannon fires a cannonball, the ball, we know that eventually hits the ground, right? Okay, he said if we increase like the force, okay, by which the cannonball is fired. So if another cannonball is fired with greater force, the purple one, with a greater force, it will go little further, but it will hit the ground, okay. So it will go little further before hitting the ground, or here the sea. Okay, if a cannonball here, this orange path or gold path, pay attention here, if a cannonball could be fired with a really great force, okay, it means here what? it could produce a speed so great, so it's fired here with a very high speed, a great speed, great initial speed. Okay, so the ball would never here hit the ground, since it would fall at the same rate of earth curvature. What this means, pay attention with me. This for sure looks like what? Like projectile motion. The ball is fired with initial speed. Okay, the greater the initial speed, see, the greater the initial speed, the farther the ball can go. Okay, the greater the horizontal distance. Okay, so if this ball is really fired with very great initial speed, the ball will go in the same way of the earth curve, so it will not hit the earth at all. I will show you another figure, it's easier. See, for example, this is the first one. With initial speed, it will go and hit the ground. If we fire it with a greater speed, it will go further, but it will hit the ground later. But if really the cannonball is fired with great initial speed, so it will go a very long horizontal distance, and it will follow the earth curve, so it will not hit the earth, and it will return back to the mountain top. Okay, so we say it will have orbited the earth. It's like now orbiting the earth. Okay, which is impossible for sure with the cannon. Okay, we can't have the situation with the cannon, but for sure we have it with what, girls? We have it with satellites. We know all satellites, they orbit earth. Even the moon orbit earth. Okay, so for the concept of the satellite is very near to this concept. So when the satellites they enter the earth at the correct great speed, they will never fall on the earth. They will continue around the earth in the same way, same curvature of the earth. Okay, and they will never fall. Okay, so pay attention with me. So when cannon fires a cannonball, the ball eventually hits the ground. This is the first one. If another ball is fired with greater force, it will go further before hitting the ground. If a cannonball could be fired with incredibly immense force, it could produce a really great speed, so the ball would never hit the ground, since it would fall at the same rate that earth curvature is produced. So now I think you should understand the concept of the sentence that I already said, that orbiting objects are in free fall. Why? Because this cannon, when it fires the cannonball at a great speed, the cannonball is in free fall, okay, toward the earth, but it will not hit the earth at all. It will continue and return back to the same place. That's why we say satellites are in free fall toward earth, moon is in free fall toward earth, planets are in free fall toward the sun. Okay, so it's actually in free fall, but it will not hit the earth because it enters the sky at the correct speed, at a very high speed, so it will continue moving. Okay, it will continue moving at the same rate that earth curvature is produced, curve of the earth is produced. Okay, so such an object is said to be in orbit around the earth. So here the concept is only that orbiting objects are in free fall, and why they are on the orbit all the time, they do not go out of the orbit, because of the centripetal force, which is here the gravitational force. So of course no cannon could do this, but we have finally achieved this work with all of our satellites and space stations, which are brought up to orbit on rockets. So this means they orbit around Earth indefinitely at fixed speed and radius. The same for all planets around the Sun. Okay, so this gravitational force is very important. This gravitational force now, so it can describe the motion of every object in space, and it is the case that every object that contains mass will exert gravity on every other massive object. So here, girls, we're saying that the gravitational force it's exerted by any massive object on another massive object. This means that, for example, there is a gravitational force exerted by me now, okay, on me, sorry, there is a gravitational force exerted on me by the laptop. There is a gravitational force exerted on me by the desk. But for sure I can't feel these gravitational forces at all, because of the masses for sure are like really negligible as compared to the mass of the Earth. Okay, I can feel the gravitational force of the Earth because the mass of the Earth is really huge. Okay, so we can feel the effect of gravity when we are only near an enormous object, a huge object such as a planet. Okay, but in reality every particle exerts an gravitational force on the other particle. That's why the best way to write the equation of gravitational force is G m1 m2 over r2. See, what is it? So here we have two bodies, m1 and m2. So these two bodies are exerting forces on each other. See, this is the force exerted by object 1 on object 2. Okay, so this object is attracting the blue object toward it. Okay, and here the blue object is attracting the orange ball or object toward it. Both are attracting each other, but we can't feel this attraction because of their masses. Okay, so how to write the correct equation for gravitational force? It is G, you will see it is just a constant. We will see it later, constant number, and you will memorize it and write it always the same thing, times m1, mass of the first object, times m2, mass of the second object, divided by r squared. What is r? R, girls, it is the distance between these two objects. From where to where we measure it? We measure it from the center of the first object to the center of the second object. Okay, so every particle, every object exerts gravitational force on another object, and so to write the gravitational force, we write it G m1 m2 over r squared, this constant number, times the mass of the first object times the mass of the second object divided by the distance between them squared. So Fg is proportional to the product of masses. The greater the masses are, the more the gravitational force, and then I can feel it. Okay, like for example me and the Earth, because the mass of the Earth is really great, so the gravitational force will be great, so I can feel it. Okay, Fg is inversely proportional to the distance squared. This is very logic. Okay, the farther you go from the Earth, the less the gravitational field will be exerted on you. Okay, the farther we go. So the greater the distance between any two objects, the less the effect of gravitational force. Distance is measured from center to center, and G, we said it is a unit, okay, and it is like this. Why the unit of it is like this? So it's very easy, we can demonstrate it here. So see, if I want to make cross multiplication, I will get that F times R squared is equal to G M1 M2. If I want G, I want to find G. So G, what is it? It is the force times R squared over M1 times M2, right? I just rearranged my equation. G equals this divided by this. So F, it's measured in Newton. Distance is measured in meters, since it's distance squared, so meter squared, right? Mass is measured in kilogram, since we have mass times mass, so it's kilogram squared. So the unit of G is Newton times meter squared per kilogram squared. Newton times meter squared per kilogram squared. This is the unit. Okay,